Okay, this is our first video on thermodynamics calculations, and you have this problem here, and you may want to pause the video for a minute and copy down this table that I have. Okay, I want to show you where the formulas are in the back of your book. If you look on the page where we had our electricity, below there, here's our thermodynamics on this side and our thermal energy on this side. We're going to be using both of these. And you'll notice if you read through these parts that there are some new terms, thermal conductivity, specific heat. Some of these terms are starting to be ones you're not as familiar with. And some of these equations, you'll notice these are starting to get more complicated than what we had before. The first thing I'm going to point out that we're going to use in several of these is a symbol that looks like this. This is a delta. And what it means is if I have delta t, let's say that's time, what this means is time final minus time initial. Delta means change in. You should make a little note of this. It means change in. So in this case, this is change in time. The final time minus the initial time. If we had delta velocity, it would be final velocity minus initial velocity. It's always going to be final minus initial, and it always means to subtract the two terms. You'll notice that there's deltas in a number of these formulas here, here. A bunch of them have deltas. That's what delta means. So we're going to use that in these formulas. I just wanted you to be aware of where this is. You'll notice that the sigma constant is here, and some of the constants we're going to have to tell you in the formulas. So these are where I'm getting formulas from that we're using, and they're in your book. Okay, so going back to our problem that we were looking at, it's really important on these problems to write down all your knowns. If you try to use it up here, it's going to be all confused. So on the practice problems, I'm going to write it out like this, and I want you to do the same thing when you work your activity problems. Write out the knowns and unknowns just like I am here on the practice ones. Okay, so then we need to just look through our problem and see what we have. Calculate the energy transferred when we put a block of hot aluminum into a liter of water. Okay, so energy transferred, thermal energy is Q, and that's what we're going to be looking for. So we're going to go through and find all the information we know in this problem, and I separated because we have two things. We have the water and we have the heat, and we're changing temperature here. So for the water, do we know the mass of the water? It's 1 kilogram. Do we know the mass of the aluminum from the problem? We don't know that. So we're going to have to find that one. Do we know the specific heat? This, I'm going to give you it in this problem because these are a constant that you would already know. The constant for water is 4184, and the units for specific heat are joules over kilograms times Celsius degrees. And this would be an information you would look up in a book that someone at some point calculated for us. We also know the specific heat for aluminum. This is 900 in the same units, joules, kilograms, times degrees Celsius. These are the same specific heat you're going to need to use in your own practice problem when you do your own. Then we have the initial temperature of the water. Do we know the initial temperature of the water? It's 25 degrees Celsius initially. And the initial temperature of the aluminum. The block of aluminum is originally 80 degrees Celsius. And the final temperature, both of them, when it all cools down, is 30 degrees for both of them end up at the end. What do we call it when everything ends up the same temperature at the end? Thermal equilibrium. And then delta T, big T is temperature, small t is time. So big T means final minus initial. So here we're going to do final minus initial, 30 minus 25, 5 degrees C here. And here, final minus initial, 30 minus 80, delta T is 50 degrees C. Okay, so what we're looking for, we already said we need to find Q at the end. That's what it asked us to find in the problem. We also don't know how much aluminum there was there. So we also need to find the mass of aluminum. So we're going to start with our formula. Of Q equals mc delta T. And this is a pretty common thermodynamics formula. You learn this also in physics. This is the formula that my students in physics always call the MCAT formula, even though that's a delta, not an A. That helped them remember it. So we're going to start filling this in, and we're going to do this formula for the water because I know all the information for the water here. And if I find the Q for the water, it'll be the same as the Q for the aluminum. So I'm going to find this first for water. So I need all these numbers here to come from the water. So the mass of the water is 1 kilogram. The C of the water is 4184 joules over kilogram Celsius. And the delta T of the water is 5 degrees Celsius. So plug this in your calculator. And we're going to get, now let's check the units. Kilograms on top and kilograms on bottom cancel. Celsius on top and Celsius on bottom cancel, leaving what units? Just joules. Energy is measured in joules. So this is the Q of the water. We also want to calculate what the mass of aluminum was that we had in there. So what we're going to do is we're going to use the same formula, but this time we're going to use our aluminum information. So we're going to do Q of the aluminum equals MCAT for aluminum. And I know how much heat was absorbed by the water is the same amount of heat that was lost from the aluminum. So we're going to plug this amount in here because we know these two amounts have to be equal to each other because the aluminum from here went to the heat from here went to the water. So this is going to be 2920 joules. We know the mass of aluminum from up here. Oh no, that's what we're looking for. The mass of the aluminum. We know the C of the aluminum. It's right there, 900. And we know the delta T for the aluminum was 50. Now, if you want to use this negative here, basically what it comes out is we lost the heat here and we gained it here. So this would also be a negative because we lost it here. So that's where that negative balances out. So that negative cancels on both sides. You know, cancel the negative on both sides. So I need to multiply these two numbers together here and then divide on the other side. So really this is what I'm doing in my calculator. And then divide both these to the other side. 900 joules kilograms Celsius. And divide this to the other side. So we divided both sides by these, so it canceled on this side and it's over here. So put this in our calculator and we get 0.46, and let's check the units. Joules and joules, Celsius and Celsius, leaving, I'm going to write the units over here, 1 on top over 1 over kilograms. Well, we know from fractions that this is really like this with fractions. And then when I'm dividing a fraction, I flip the second one when I multiply. So it really comes out looking like this. So my final units are kilograms, which are in fact the correct units for mass. Now I probably wouldn't leave it 0.69 kilograms. I would take and convert this over to grams by moving it over 3, and we would get 460 grams of aluminum. And we're done with that problem.